Hey everyone, so welcome to our Compro for ANSYS training webinar. My name is Sanesh Iyer. I'm an applications engineer here at Convergent, and the Compro for ANSYS integration is one of the main projects that I work on. So I'm looking forward to introduce to you some new features for Compro for ANSYS, and hope you enjoy the presentation. So in today's agenda, I'm going to go through an introduction to Convergent, an introduction to Compro for ANSYS, and describe some of the workflow as an outline for Compro for ANSYS, and then get into a tutorial. So I'm actually going to do a live demo. I've cropped out the waiting for the simulation to run, since each simulation takes about 12 minutes to run. But other than that, it's live, and walking through a tutorial on how to do a thermochemical flow compaction and stress deformation results to predict process-induced deformation. So an introduction to Convergent. So Convergent Manufacturing Technologies, our main office is located here in Vancouver, British Columbia. We have two offices here, and we do a whole suite of products and services related to manufacturing of composites materials. So we have Raven, which is our standalone, fast and easy to use solver. This is a very useful tool. I find many people gravitate towards Compro, which is our finite element plugin, which allows you to supercharge finite element with composites process simulation, but I find Raven complements it quite well, and these two, when working together, actually you can be very efficient and ensure your full-scale finite element results give you the results you're looking for, and make use of Raven for things like cure cycle design and material analysis. We do offer process monitoring hardware, so Coho, which allows you to do gas flow and vacuum leak detection in your systems, and location of your vacuum leaks, which is quite cool, as well as CERT, which automates the specification assessment, so you can ensure that your part is meeting your manufacturing standards and meets qualification standards as well in an automated way. We do offer engineering services as well, so engineering program support, any process analysis and design, as well as any training and education required for composites processing and any of our products and services. And of course, to feed our simulations, there's materials characterization. So for this, we have a software called Cremoti, which allows you to do a model fitting workflow for various composites models, so cure kinetics or viscosity or whatever else it may be. We can use Cremoti to do those characterizations and feed those results into Raven or Compro. We can also do the testing and model fitting for you as either an off-the-shelf or customizable solution in our full laboratory here. So a little bit of a history of Convergent. Convergent actually started as a set of PhD theses at UBC as Compro 2D before 1997. And then Convergent was founded. And since we've been founded, as you can see at the bottom of the timeline here, we've worked with a number of government projects, including the Air Force Research Laboratory and DARPA and NASA in the US. We've worked with the National Research Council of Canada on various projects over the years as well, and the Eureka projects, some of which are international collaborations as well. So we work worldwide. Our government and our customer affiliations are worldwide as well. Over the years, we've released Compro 3D, Raven, Coho, Cremoti. We've talked about those. We opened our second Canadian office, and this is our laboratory, as well as sister company Convergent US. So for any of the US customers, there is a dedicated US office. And we're involved in other projects such as the Learning Factory Digital Twin UBC. So a core component to our software offerings is the common component architecture. So our material properties are state variable based and based on an expandable material database. So we have over 140 constitutive models integrated into our common component architecture. So everything from cure kinetics to viscosity to CTE to shear and tack. And we have the largest high fidelity composites materials library anywhere. There's over 30 open data sets, 40 proprietary data sets created for customers, and they have available to them, and more even proprietary data sets, and then 10 distribution C data sets which are created for and managed on behalf of these government for their contractors. Now, the beauty of this common component architecture is it lets us take external data, so material characterization data from Cremoti, any user-defined material constitutive models, or any third-party research codes. Feed data into our common component architecture for material properties, and then report those out to our different software tools. So Raven, our 0D, 1D, and 2D standalone solver, our Compro interface for finite element software, CPATA, which is a plugin for CATIA, as well as our forming plugin as well, which interface directly with CAD software. So the beauty of this is, thanks to the common component architecture, all of our software offerings take the same material data and are based on the same physics engine, allowing you to quite quickly do multi-scale simulation and allow different user types. So whether you're a materials and process engineer, research and development engineer, or even a designer, you can use the same physics to inform your model and your optimization processes. At Convergent, we believe in a simulation scale up, and we follow that with the way that we build up our models. So as we'll see in a second, all of our models are built up of matrix and a fiber file. So your matrix and your fiber. And we build these up to the lamina scale. We can include architecture, so we can build up not just unidirectional, but plane weaves or 8-harness, whatever it may be, and simulate these all the way up to the 3D scale, full scale spar here using finite element software. And we can simulate all of these steps as well. So Raven 0D we call this a virtual DSC. It gives us a point solution for material properties and how they evolve using a cure cycle. Scaling up to the laminate level, we have Raven 1D, so we can actually do a drill through of a part and look at the thermal gradients, evaluate for potential exotherms or thermal legs, and do parametric studies to optimize our cure cycle. And similarly, we can do that 2D in Raven, so we can see the thermal gradients associated with heat transfer coefficient gradients in our part, or part geometry differences as well, and then scale that up all the way to 3D in Compro too. So full multi-scale modeling for everyone from the finite element user to the materials and process specialist who, without finite element experience, can still use this advanced physics to inform their design decisions. Now we integrate with multiple workflows for composites process modeling. This is the DESO workflow, where we start in CATIA to define your geometry and your layup and your mesh. Using Composites Link, and put this into Abacus to apply loads and boundary conditions and contact. And then the Compro plugin allows us to perform curing simulation and process induced deformation analysis. And we can port this back to CATIA for tooling compensation using Realistic Shape Optimizer. Now, of course, this is the ANSYS presentation. And we can do the same thing with ANSYS, so we can either generate a design in SpaceClaim or import it into SpaceClaim. We can defeature a model as necessary in here as well. Optionally, you can use ANSYS Composites Prepost to define your layup and draping. You can use ANSYS Mechanical to set up your model, boundary conditions, and loads, and if you haven't used ACP, to find your mesh as well. And then Compro takes care of the cure, can calculate parameters such as porosity, flow compaction, and process-induced deformations. And then again, we can feed this information back into SpaceClaim to perform a tool compensation. So in multiple packages, we have a fully integrated workflow with for using composites process simulation to improve your design and your part. So an introduction to Compro for ANSYS. So again, Compro is a simulation platform. It plugs into Abacus, ANSYS, and OpenFEM to take advantage of the latest finite element features, and can answer the question, will your part meet your engineering specifications? What those specifications are, it could be porosity, could be process-induced deformations, it could be thermal profiling. There's actually many questions we can answer with Compro, and today we're going to go through primarily predicting the thermal profile, the consolidation, and the spring-in or the dimensional conformity. So thermochemical analysis is the base analysis type. This studies heat transfer in the part, so any effects due to heat transfer coefficients due to your curing environment, whether that's an autoclave or an oven or heated tooling. Thermal effects of your tool, any exotherm due to your resin. So we can see here in this example on the bottom, there's a thermal lag between the air temperature and the part. And then as we reach the hold, we actually see the exotherm, because in this case, the part is thick, so it exceeds the air temperature and then comes back down for the hold. So of course, we want to make sure that we don't have big thermal gradients on our part, that our lags are not too large, and that our exotherms are not non-existent or not severe. And then as we see in the 3D model, there's some thermal gradients within our part, as well as within our tool, which may affect our the robustness of our process as well. The next analysis type is the flow compaction analysis, which simulates the flow of saturated resin through a porous fiber bed. So of course we have our fiber bed, which consolidates when we apply pressure, and this changes the permeability of the fiber bed. Our matrix is also curing, which changes the viscosity as well. So there's many factors going on here. And this can be used to answer such questions as, what is the volume fraction distribution? And what is the resin pressure? And what is the thickness of the laminate in the final part? And in particular, fiber volume fraction and thickness can lead to significant quality issues in your part as well. So it's important to have a good understanding of these, which we can do through the flow compaction analysis. Stress deformation analysis is the last analysis type that we're going to cover today. And this includes the internal stress development in the part, taking into account the final part shape after tool removal. So including CTE mismatch between the resin and fibers, CTE mismatch between the part and the tool, cure shrinkage of the resin, any viscoelastic stress relaxations, et cetera, et cetera. So what this can predict is the spring in of curved sections, the warpage of flat sections, any residual stresses in the part. And as we can quite clearly see on the right here, there's the deformed shape and the initial shape, and there's a gradient between these two. So this may or may not be acceptable in your manufacturing tolerances, and by doing a stress deformation analysis, you're able to compensate these before you actually go and machine your tool and invest time and money in capital expenditures. So Compro for ANSYS is a supercharger for process simulation of composites. And again, it includes the hundreds of material models through the Convergent common component architecture to be used inside the ANSYS mechanical environment. So we get the best of both worlds. We can use all the latest solver and GUI interface technologies from ANSYS, and we can also support advanced material modeling through Compro. Now, getting a little bit into the details of how the integration works, there's 4 key components. The first is the Compro CCA libraries, the .dll files, which execute the process model. So this actually contains all of the material models and the mathematics and physics running in the background. These are installed for you when you run the Compro installer. The other item that you'll have to install through ANSYS is the Compro for ANSYS plugin, which is a .wbex file, workbench extension. And this is the graphical user interface for the GUI, which automates the link between ANSYS and Compro CCA libraries. So this is actually what's going to pop up, and this is what you're going to interface with, is this plugin. Another piece of the puzzle is the material data files. These are specific to Compro CCA, so to run Compro, you need Compro CCA material data files, and these contain all of the parameters for those many advanced material models. You can use the open materials available from Convergent if they're available to you internally in your company or from your supplier as well. If they're not available to you, please contact us, and it's possible for us to characterize them for you or support you in characterizing them yourself. So it's imperative for a simulation that you have good data, and Compro CCA material data files provide you with that data. The last piece is the CCA configuration.xml. And this is a file that's automatically created by the plugin, but it's important as it maps the materials between the plugin and ANSYS. So it provides a link, kind of a map between the two. Thanks to this, you can do simultaneous materials simulation using Compro, so you can have multiple materials within the same laminate or same simulation. So say if you have a carbon fiber prepreg laminate with a glass veil, you can simulate the glass veil and the prepreg using Compro. Or if you have a specific tooling that you'd like to simulate using Compro as well, you can do that too. So there are a number of features available in the CCA configuration file that can include things like defect porosity and various smearing to make your simulations more efficient. So for more information on the CCA configuration file, please refer to the documentation or contact us directly. The Compro for ANSYS plugin again acts as a link between the DLLs and the ANSYS interface. So when you click a button in the Compro plugin, what it's doing is making modifications to the input or the ds.dat file in ANSYS parametric design language, or APDL. And it does so by inserting command snippets. And these command snippets I've shown here, you can see the arrows pointing to them. And these do various things like change element types and set specialized boundary conditions and loads. So if you have a pore pressure boundary condition and load, for example, it also lets you call user material subroutines, et cetera, et cetera. So yeah, various things that these snippets do. If you want more information, it's inside the documentation again. You don't need to worry about it though, it's all taken care of by the plugin. Also done is change solver settings. So Compro requires a number of solver setting changes, and the plugin takes care of these for you as well. So the plugin really automates these processes. You know, the way that traditionally we've done this is by inserting these command snippets manually, which can be quite time consuming and tedious. So this really streamlines the material mapping and command snippet insertion. So making it much faster for finite element users to use ANSYS and Compro to run process simulation models. So the plugin interfaces with ANSYS using various toolbars. So on the bottom left, there's the toolbar in Workbench, and on the bottom right, there's the toolbars available in ANSYS Mechanical. And the beauty of this workflow is it actually lets you use all of the traditional tools available in ANSYS. So if you want to define your material assignments using ANSYS Mechanical tools or ANSYS Composites Pre-Post or ACP, you can use those tools as intended by ANSYS. So if you're trained on those tools, it's not a significant extra burden of adding Compro into your workflow. And the plugin again generates that CCA-configuration.xml file to ensure the correct material mapping, regardless of the workflow used to assign materials. And it inserts the command snippets and solver settings. So these buttons do some very convenient things for you. I'll also bring your attention to the Compro Tools toolbar. The print point cloud button is very useful for performing tooling compensation. If you have predicting the process induced deformation and would like to use that information to compensate your tool, you can use that button. Pore pressure boundary condition is nice for flow compaction analysis because you can apply a bleed condition. There's various boundary conditions and initial states related to porosity, and specifically multiple species porosity included in here. And some useful boundary conditions related to nodes, orientations related to nodes as well. Quite like the match node to elemental coordinate system button is, changes the way that some results are plotted, making it more intuitive to interpret as they're plotted relative to the fiber orientation rather than the global coordinate system. So for more information on what those buttons do and how to use them, please see the Compro documentation. So what does the workflow look like for Compro for ANSYS? The Workbench setup process is quite simple. We drag and drop the analysis systems to form our correct workflow. And ANSYS Mechanical is up top, so we just feed the geometry into our first model and the engineering data into our first model, the thermochemical simulation, generate our mesh and material assignments here, and map our model and our results forward. Compro takes care of the results mapping between the transient structural and the static, the stress deformation, or the flow compaction and the stress deformation, which is why we don't see a link here. ANSYS ACP looks a little bit different. We have to be careful to make sure that we connect ACP uniquely to the model of each analysis system. So the ACP connects to thermochemical, ACP connects to flow compaction, ACP connects to stress deformation, and the same for the tool mesh, which is generated in a separate mesh module. And additional training on ACP we can provide upon request. However, other than actually generating the mesh and performing the correct workflow, it is quite similar. Once you save your file, You'll create a user files directory, so your project name underscore files / user files. Create a CCA data directory, CCA-data, and put your material data files that you want to simulate. So your composite and your matrix and your resin and your fiber files in there. Then when you click create and load compro material library, it's automatically going to insert this engineering data block with all your compro materials in it. In ANSYS Mechanical, we generate and assign our materials. This also can be done using an ACP. Select the correct compro analysis type, apply the compro, the requisite boundary conditions and loads, and then we solve and analyze and repeat steps 2 to 4 for each analysis module. And as you'll see, it's quite straightforward, as long as you, of course, have a good understanding of what your boundary conditions and loads are, so your cure cycle and how to prevent rigid body motion of your model and apply appropriate friction and so on. Setting up a compro simulation with the plugin is quite straightforward. So now I'm going to open up ANSYS Workbench and move on to the tutorials component, and we're actually going to do a full workthrough of a thermochemical flow compaction and stress deformation simulation. Hey everyone, so now we're going to work through the tutorial component of the webinar. So you can see I've already gone File, Save As, and saved my Workbench project as training example. I'll show you the directory. So I've got my training example Workbench project, the file folder that's automatically created to it, and in here I've got my user file directory as well. In this folder I've also got my claim, geometry, as well as my cure cycle. So that's cure cycle. It's just an Excel file with my time, heat transfer coefficient and temperature, time and pressure, and also some notes for X gel and T gel. So I like to just have an Excel file like this open just to help me with some note taking while I'm running these simulations. So getting started, the first thing that I'm going to do actually is go back into my File Explorer and take the CCA data folder, which contains all of the different material data files that I need. So the composite, the fiber files that are necessary, the matrix files that are necessary. And I've also got a tooling file in here in the case that I wanted to run compro tooling material as well. So you can run compro for curing and non-curing materials. But in this case, I'm going to show you how to run compro for ANSYS with a mix of curing materials using compro and non-curing materials using ANSYS. So to start, right-click and copy CCA data, navigate to user files, and I'm just going to place that folder here. I'm going to go back to Workbench and click create and load compro material library. Great, so I have my material library here, and when I open this up, you can see I've got my composite, my tooling steel from compro, and structural steel. Note that the properties in here are just stand-in for these because it's actually the material data files which are being called. Perhaps I can show you an example. So when we call a compro material, it's going to call these XML files which contain density, CTE, cure kinetics, permeability, modulus, et cetera, models, which are specific to the common component architecture for compro and Raven, etc. So going back to Workbench, go back to my project. I'm going to now insert a geometry component system and right-click, and I'm going to just import my reference mechanical geometry. I'm not going to open space claim, but I will show you what that looks like in the step. So next, I'm going to add my transient thermal. Actually, let's rename this to thermochemical. Pull in the engineering data, pull in the geometry. I will refresh the model. And that may take a second. Still going. Aha, now we're done. So now I'm going to bring in a transient structural system for flow compaction. I'm going to map the model forward here. So what this is going to do is any work that I do in the transient thermal model, it'll automatically carry it forward to the flow compaction. And then a static structural analysis system. And map the model forward. And this static structural analysis system is going to be for stress deformation. There we go. So I've got my workbench layout for ANSYS, for meshes generated in ANSYS Mechanical done here. So perfect. And the next thing we're going to do is open up ANSYS Mechanical by double-clicking on the transient thermal model so that we can set up our mesh and material assignments. So now that we've double-clicked the model for the thermochemical step, we're going to open up ANSYS Mechanical. So we have our zoom out a little bit. We have our L flange geometry, the L and the tool. First, I'd like to assign materials. So the L, I want to make a curing composite. And the tool is I'm going to leave as the ANSYS structural steel default. Now you can run any combination of Compro or ANSYS materials using Compro for ANSYS. So you can run Compro for the curing materials and ANSYS for the non-curing materials. You can run Compro and ANSYS for Compro for the curing and non-curing materials. A combination you'd like. If you're using ACP, you can apply different materials to different layers. So it's all the material assignments you can use doing the traditional way, so long as you import them using the create and load Compro material library button up here. Cool. So materials have been assigned. Next thing I'm going to do is generate the mesh. So I'm going to apply a sizing constraint because I want at least 4 elements through thickness. So I'll click on my edges. Thickness edges. And you have to zoom in because they're quite small. Great, that's all 4. Change this to number of divisions. Change it to 4 divisions, 4 elements through thickness. I'd like to refine my corner. So change that view a little bit. Apply another sizing condition. Change this to box select and drag from right to left to select all of my corner edges on the part and the tool. Change this to 12, nice and refined in there. And I'm going to change the sizing as well. So the sizing I'll apply to the body. So I'm going to set 5mm element size for the laminate and slightly less dense for the tool. Let's say 1 centimeter. So, see, that's not what I meant to click. So let's generate my mesh. See the mesh here. Nice structured mesh in the laminate with the good accuracy in the corner and through thickness, and a relatively coarse mesh in the tool so that we don't increase the computational burden for no reason. And the next thing that I'd like to do is insert my element orientation. It's important that you insert the element orientation if you're generating meshes in ANSYS Mechanical. If you're using ACP, ACP takes care of this for you. So of course, I need to apply element orientations to the laminate, and this corresponds with my fiber directions. So here I've selected that body. For the through thickness direction, I'm going to select the top surface. That's the 3 direction of the laminate. And for the x-axis, I'm going to select the edges along the side here to be the 1 direction. So for this laminate, my fibers will be running along this top surface. I'm going to generate the orientations, and if I zoom in, you see that the blue through thickness direction follows the normal, and the x-axis follows that as well. Perfect. So we've now finished the meshing and material assignments. ANSYS Mechanical. This can also be done using ANSYS AP, and if you'd like additional ANSYS ACP training, please contact Convergent. So next, we're going to move on and set up the actual thermochemical simulation. So to begin setting up the thermochemical simulation, we're going to go to Compro Analyses and click Thermochemical. And this is going to insert a whole bunch of command snippets and change solver settings for us. If you are interested more in what Compro is doing, you please read the documentation. But for now, all we need to remember is that we want our L flange to run with the composite. So we're going to leave the Compro on off snippet as is, unsuppressed. But the tool we want to run using an ANSYS material, so we're going to turn this off. So right click, suppress, nice little X here. And so we see that Compro is on, checked for the L, and off, crossed for the tool. That's perfect. So the next thing that we're going to do is insert some boundary conditions and loads. So here I can go and apply to my symmetry faces on the inside. I'm going to apply an insulated boundary condition. And then all external faces, I'm going to apply a convection boundary condition. Let's make sure to get all of the external faces. So the beauty of doing this in 3D is if you do have curing environment gradient, so you've done some analyses and you know in your part, especially for big parts, you have differences in heat transfer coefficient or thermal cycles on different parts of the laminate, you can subject them to that as well. So in this case, it's quite a simple example, but of course you can use all of the tools and apply spatial gradients for boundary conditions and loads in ANSYS. And Compro will take those into account as well. So we'll apply it to those faces. The next thing that I'm going to go to is my analysis settings. I just want to set the simulation time, so I'm going to open up that handy Excel file I have. I see my cure cycle is 18,257 seconds, so I'm just going to copy that in here. Now this is a transient analysis, so I do want to take control over my time step settings here. So I'm going to set the initial time step to 100, the minimum 100, the minimum to 1, and the maximum to 250 seconds. You do want these to be quite refined. Otherwise, your simulation will not have accurate accuracy through time. The next is a supplier thermal cycle. So again, going back to our handy Excel file, have this here, copy it, paste it. So we have our cure cycle in green. So 2 holds, 2 ramps, and back down to the base temperature. And we have a uniform heat transfer coefficient throughout time. Great, so that's our thermal simulation set up, ready to run, and we can just click solve, and now all we have to do is wait for the results. Now, while the results I'm waiting for those, I'm just gonna take down some notes. So the next step we're gonna do is flow compaction. And for flow compaction, I need to know the time of gelation, and for that I need to know the degree of cure of gelation. So I'm gonna open up the material file, and I'm just gonna search DOC, or gel rather. So gel at degree of cure, sometimes this is called xgel. So you can see what that parameter is called in the CCA documentation. So in this case, I see it's 0.4690, so I'm just gonna copy that and make a note of it in my handy Excel file. Didn't copy the right thing, but 0.4690, perfect. And so these CCA material data files contain all of the different models. So in the case of this matrix, we have cure kinetics, modulus, Poisson's ratio, cure shrinkage, et cetera, et cetera. So I'm going to Go back to mechanical. Simulation is done. So that was quite quick. So the first thing that I'm going to see is my degree of cure plot. You see we have a nice degree of cure gradient. It cures faster on the edge of the part, of course, because we apply heat transfer to the edge outside of the part, but not to the inside. In part, we see it's on the order of 0.2. I can also insert a thermal temperature result. Evaluate that. So we see actually that this isn't great. If we look at our convection, we see quite ramps and holds with quite sharp corners. Ideally, we want our part to follow exactly our specified cure cycle. But when we look at this, there's quite a lot of thermal gradient in the part. There's quite a lot of lag. These ramps are slower than intended and not reaching the hold temperatures desired at all. In fact, we don't even reach 180 degrees heat cure. So, we might want to redesign our cure cycle. We might go back here and say, we need slower ramps and longer holds, or some combination of the two. Maybe we need intermediate hold, or maybe we need to redesign our tooling. We need less thermal mass in our tooling, or if it's severe enough, maybe we need to consider different curing equipment as well. So, many things that you can see are possible issues here, and it's important that these match your design requirements and your internal specifications or your material manufacturer specifications for how it's cured. So in this case, since it's a demo, I'm not going to revise this, but if you want more information on how to design and optimize your cure cycle, please contact us or look in our documentation. Raven is also quite a useful tool for doing this without going through the full finite element environment if you want to evaluate a simpler case. So great, we're now done with our thermochemical analysis, setup and results analysis, so we can move on to flow compaction. Close that, now back to Workbench, just make sure everything is updated. Perfect, all checked. So now we're ready to move on to flow compaction. So now I'm just waiting for my flow compaction simulation to refresh. I'm gonna right-click and edit this to open up ANSYS Mechanical again. So this again may take a minute. Great, so here's ANSYS Mechanical. I can zoom in on my part. Again, I've got the geometry here. So the first thing that I'm going to do is I'm just going to group the old command snippets and call them Thermochem CS, just to keep them stored out of the way. Thermochem CS. And this is just organizational. You can skip that step. I like to do it for organization. So, next step, clearly, we're going to go to click Compro Flow Compaction. It's going to insert our flow compaction command snippets. And also note that it's suppressed our thermochemical snippets, this little X, which is perfect. Those are snippets from the thermochemical analysis. We don't want those influencing our flow compaction analysis. So again, we want to turn off Compro for our tool. We also want to insert an element orientation again, so that's not carried forward. The mesh is, however, carried forward, so you just need to reassign the fiber orientation. You don't need to assign a fiber orientation or element orientation if you're using ANSYS ACP to generate your part mesh. ANSYS ACP takes care of that for you. Generate our orientations, boom, same mesh, same orientations, perfect. So now, we forgot to do something in our thermochemical analysis and thermochemical results, which was to investigate our time of gelation. So the flow compaction analysis studies the pre-gelation behavior of the composite. So when you apply your consolidation pressure and the viscosity evolves and your permeability evolves, it studies the resin flow or redistribution in your laminate, which can lead to volume fraction changes or laminate thickness changes as well. So it's important to know that information if you're looking for a high degree of fidelity in your predictions. Now, because this all happens in the pre-gelation regime, we only need to simulate in the pre-gelation regime. So, in this case for our transient, for a thermochemical analysis, we ran the full cure cycle of 18,257 seconds. But here, if we go back to our handy Excel file, remember degree of cure at gelation is 0.469. So if I go back to thermochemical, and I look for the first instance of 0.469, 0.4. So at 11,000, so I'll say here at 11,346 seconds is the first time I exceed gelation. So this is where I'm going to stop my simulation. So I'm gonna quickly write that down here. 11,346 seconds is my time of gelation, and that's how long I need to run my flow compaction analysis for. So I'll go to my analysis settings, 11,346. To find my time steps again, I'll use similar ones, 100, 1, 250. Compro has taken care of the rest of the solver settings for me. I'd like to change my contacts to frictional. Since this contact was imported, I can't edit it, so I need to duplicate it. Suppress the old one and go here and change it to frictional. And I'm going to use a friction coefficient of 0.15. Now, if you're interested on how to characterize your friction coefficient between your part and your tool, please contact us directly. And often we need to adjust the normal stiffness here to get convergence. So usually we recommend changing this to a normal stiffness factor of 0.1. And again, if you would like to investigate more into this, please contact us directly. So our analysis settings and our contact have been set. We've set up our element orientations, our compro on off snippet. The next thing is to apply our boundary conditions and loads. So if I go to the model, add displacement so on this bottom surface, it's normal to the y-axis. So I'm going to apply y. Then on my symmetry faces again, I'm going to apply, in this case, it's normal to the z-axis, so 0 z displacement. And here on the last axis, it's x displacement. So I've now blocked rigid body motion. I'm going to rename these a little bit more clearly. X, BC, Z, BC, Y, BC. Next, I want to apply my pressure cycle. So to the top surface only, the laminate. And I'm going to go back to my handy dandy Excel notepad, copy my pressure cycle. Actually, I don't need my thermochemical analysis anymore. I can close that. And I'm just going to paste it in here. So you can see over the first 500 seconds, I ramp to 1 kilopascal of pressure. And then I didn't have 11,346 in my cure cycle. I had different increments, but ANSYS is smart enough to interpolate this automatically for me. So I've applied my boundary conditions and my loads for flow compaction. The next thing I need to do is go back to Workbench and map forward the thermal history, which is super important. So this imports the thermal history generated in our transient thermal simulation into our flow compaction analysis. So we see here now we have a new imported load, imported body temperature, and we just want to make sure that this is importing the source time at all time steps. There we go. So we can see I'm now importing it at all time steps, and it'll interpolate between those uh, as specified. Perfect. So my flow compaction analysis is now set up, ready to run. As you can see, that was quite straightforward, especially since we could carry our mesh forward from our previous analysis. The last thing that we do need to check is our initial volume fraction. And so if I go back to my, let's open up my composite material file. So you see in composite material file, I actually specify a fiber volume fraction of 0.574. And this is the fiber volume fraction after cure. So this is your cured part fiber volume fraction. Now, probably the fiber volume fraction if your laminate is different. The ANSYS for Compro plugin for any material will default to this number, and it's important that you set it to a realistic one so that you could measure yourself, or again, contact us if you'd like us to measure it for you. So in this case, I'm gonna say it's initial fiber volume fraction of 0.6. Cool. And then we don't need to worry about it for the tool since Compro is not being called for the tool. That command snippet won't do anything. So great, we're now ready to click. So go back to the solution. 4 cores, distributed is unchecked. Now we're ready to solve. So while that's running, I just would like to show the contact tracker. So remember, if we go back to our contact, we set a normal stiffness factor of 0.1, which could lead to more penetration. And penetration is when you have the surfaces moving through each other. So I'm just going to plot my penetration chart. And I just want to make sure that the penetration, especially in the next step, the stress deformation step, is orders of magnitude below my deformation. So I'm expecting deformation on the order of millimeters. My penetration is 10 to the minus 4 below that. That's probably okay. That's up to the interpretation of the analyst. But when you're changing this normal stiffness factor, please be careful and check your penetration, because if you're trying to achieve convergence in your contact by changing your normal stiffness factor and you're causing too much penetration, your results will not be sensical, of course, because your tool and your part are deforming through each other. And here we can also look at the force displacement convergence, or displacement is converging nicely, or force is converging nicely as well. Yeah, so at this point, I'm going to cut straight to when our analysis is done, because this simulation will take a little bit longer, about 10 minutes. So we will be right back as soon as we have results. So our model is now run. We can take a look at the solution information, the solution statistics to see how long that took. It was 11 minutes it took for that. So because it's a transient analysis, all of these analyses are transient. It takes some time because you need to resolve at each time increment, and those time increments need to be quite fine. So now, again, we can plot the degree of cure. That's done by default. Let's get a nice view here. So we can see the degree of cure, of course, is only plotted for the laminate. And this is just because the laminate is curing and the tool is not. We'll also notice that we don't cure fully because we terminate our result at gelation. So our maximum is 0.4669. So just before gelation, we remember our gelation is 0.469, but this effectively is the end of our cure. Now, some things that might be interesting for us to add are a user-defined result for pore pressure. So press. Name that to pore pressure. So we can view the buildup and relaxation of pore pressure in our laminate due to consolidation and the permeability changing as well. We can also look at our state variable list that Compro prints out here and look. So not all of these are going to be available. You know, we didn't do a integrated IFS 3P simulations. We won't have access to gas volume fraction, but we will have access to, you know, viscosity and fiber volume fraction, which are of interest too. So if I go ahead and plot viscosity, so state variable number and the name. So state variable 6 and 7 are viscosity and fiber volume fraction that I'm interested in. So insert user defined result. So SVAR 6 is viscosity. And perfect. So we see that we have a small change in fiber volume fraction due to consolidation. We have viscosity gradient. Of course, it's as it reaches dilation, it becomes quite viscous. So if we plot just before that, here, let's play the video. You can see. Well, so we can see our orders of magnitude here are quite sparse. So if I make the maximum closer to, let's see here. Rarely do we go above 100. So I'm just going to plot from 100. So we can see there's more of a gradient if we plot in that regime. And if we reduce this even more to 50. Yeah, so viscosity history, fiber volume fraction as well. There's a gradient. In this simulation, we didn't apply a bleed condition. You could apply a bleed condition using the pore pressure boundary condition, which you would see a different result there too. So yeah, that's our flow compaction analysis. Now something that I would like to show you is go back to our user files. There is this file.ist that is created. And I'm going to edit this with Notepad++. So this file.ist file is the initial state file, and it contains state variables that are being mapped forward. So if you remember again, our fiber volume fraction was state variable, should be state variable 7. Let's double check that. So variable list, fiber volume fraction is 7. So we go back to Notepad, state variable 1, 2, 3, 4, 5, 6, 7. So at each node in an element, or each integration point, depending on how you choose to set this up, it's going to map the fiber volume fraction forward to the stress deformation simulation so that you actually get an accurate fiber volume fraction gradient simulated in the stress deformation step. So the beauty of this is we've mapped forward our thermal gradient, thermal history from the transient thermal analysis, and using a flow compaction analysis, we've generated our consolidation and our fiber volume fraction gradients, and we can map that forward to get the most accurate prediction of process-induced deformations that we can. So now we're done our flow compaction analysis. We can close this, go back to Workbench, make sure that everything is updated, and move on to our deformation system. So now with our flow compaction analysis system complete, we can move on to our static structural stress deformation model. I'm going to open ANSYS Mechanical. And so in this last step, I'm going to plot, predict the process-induced deformations. Perfect. So as before, zoom in, I have my L, I have all my old command snippets. So I'm just going to group the flow compaction snippets. Flow comp CS. Again, this isn't a mandatory step, but it helps keep things organized. Great. And I'm going to click stress deformation. Now you'll notice there's other analysis types here, diffusion drying and IFS 3P multiple species that we've not talked about. And again, see the documentation or contact us for more if you'd like to run other analysis types to solve other types of problems. So you can see I've got my frictional contact here again, same. Now this is imported from the previous step. Added a contact snippet. I'll explain in a second what that does. I need to turn off the compro snippet, suppress it for the tool again, and I need to remember to reassign my element or my fiber orientations. Make sure to select the right edges there. Done. Generate my orientations. Perfect, just as I expected. Great. So now I just have to set up my boundary conditions and loads. So I'm going to work through these boundary conditions quite quickly because they're almost the same. So again, we need to fix rigid body motion during cure. So that's normal to the y direction. That's normal to the z direction. And this is normal to the x direction. Great. So let's rename those again. Great. So now I'm going to go into the analysis settings. So you can see here now Compro has created a second step for me. So I'm going to navigate back to so I know my cure cycle again is 18,257 seconds long. So I'm going to add an extra second for the second step. The second step is where I do the demolding. So 18,258, and for the first step is 18,257. So let me, take a second to walk through exactly what I'm doing here. So the first step is our cure cycle. This is our temperature and pressure load applied to our part. The second step is tool removal, because of course to predict process-induced deformations, we need to predict how the part is going to spring in or deform when it's off of the tool. And the way that we do that is actually by removing the contact. So in the first step, we simulate the cure again with applied pressure and temperature cycle. And then in the final step, we delete the contact. So we allow the part and the tool to move through each other. And this simulates demolding. So obviously when you demold, there's no interface between the part and the tool. So the second step just needs to be 1 second long. The time of the second step doesn't matter. However, the first step, it does. It should be the same length as your cure cycle. So again, we want to turn on time stepping by time. We'll set this to 100 seconds initially, 1 second minimum to 50 seconds maximum. And our second step, I'm going to change this to automatic time stepping. And I'm going to say that I want a minimum of 10 sub-steps to solve this, but I will let it go to a arbitrary large number as well. Now, because I'm deleting the contact and the tool removal step, I no longer have a fully constrained model, so I'm going to hide the tool here. So this is how the model will look in the second step, effectively. So we can see that, again, if I highlight my loads, we have a XBC and a ZBC, but we don't have anything preventing motion in the Y direction. And that's important because otherwise it's going to just move freely in space. So I'm going to apply a displacement condition to this edge on the intersection of the tool surface and the symmetry plane and apply Y. And I'm going to turn this off for the first step. So I want it to move freely with the expansion and contraction of the tool in the first step during the cure cycle, but then be fixed in the second step. So we can see that now it's suppressed in the first step and on in the last step here. So that's perfect. We've set up our boundary conditions. I'll rename this to part demold YBC. And also I'm going to print point cloud. And what this is going to do, similar to all of the snippets in here, is going to create a command snippet that has some content and a name selection. So the name selection is what the command snippet acts on. In this case, it's print a text file with the nodes and the deformations of those nodes. So let's say I want to print out this bottom surface. I'm going to select that, and that's going to print out that result for me. Perfect. So the next thing that I have to do is apply my consolidation pressure, of course. And again, I'm going to go up to my handy Excel notebook, paste those in. Paste those in here. And of course, during demolding, we've debagged this, so I want to deactivate the applied pressure. I don't want any applied pressure in that step. So we now have our command snippets, our element orientation, our contact is set up from our previous simulation. We have the other command snippets. We have an export surface. We have our boundary conditions for the cure cycle and the additional boundary condition for the demolding step. We have an applied pressure. And of course, last but not least, we need to map forward our cure cycle, or our thermal history rather, into our model. And we need to remember to change our imported load to all times. And that's now done. Perfect. So we're now ready to run. So let's go back to solution, uncheck distributed, 4 cores, and click solve. So now the simulation is running, and we will be right back with the results. And again, here you can look at your contact tracker if you like, penetration or max normal stiffness, penetration. You can look at your force convergence, etc., etc. So I'm going to let this run, probably be another 10 minutes or so, just like the previous simulation, and we'll be back when it's complete. So the simulation is now complete. You can look at the statistics here to see how long that took. 5 minutes, so quite quick, less even than the flow compaction. So again, we can see our degree of cure here. We have the same gradients we observed before. One result, of course, that we're interested in is the process induced deformation. So I'm going to plot the total deformation for the part at the last time step. And so, of course, our minimum displacement is on our corner that is fixed on the y-axis and also on the symmetry plane here, and it grows outwards from there, which is exactly what we expect. If we look at the vectors here, we see that most of the deformations are normal to the surface, which is consistent with the spring-in that we expect due to cure shrinkage and CTE mismatch in the corner. So those results are exactly as we expected. Now, one thing that I like to do is plot this in true scale, look at it from the side view, and plot the undeformed model as well. So we can see again that there's spring in and there's a small amount. And again, it's up to you as the user to define what is an appropriate amount of tolerance or spring in. So using this data, there's various things we can do. Going all the way back to thermal design, your cure cycle, and ensuring that you're not gelling during a ramp, or minimizing your gel temperature too can also help reduce your PID. If you want to use tooling compensation, so one of the various workflows you can actually compensate for the process-induced deformations if your cure cycle and your part and your tool are all set in stone, you can do that as well, and that's what this export surface is useful for. So if I open up the solver files directory, you can see that I have this export surface1.dat. I'm going to open that in Notepad++. And this is a file that contains our node position X, node position Y, node position Z, deformation in the X of that node, deformation in the Y of that node, and deformation in the Z of that node. And that's all documented in the user manual. So using this, you can plot these results using an open source tool like Cloud Compare, which is quite convenient for doing statistical analysis or comparing these to scanned results as well. If you'd like more information on how to do that, please do contact us. And as well, you can use that point cloud for various tooling compensation tasks. So now we have predicted the thermal history of our part using a cure cycle and a convection boundary condition. We have seen that clearly there's some issues with the cure. I can plot this here as well, actually. The user defined result, and BFE is our temperature. So we can see clearly that there is thermal gradients in our part that are undesired, quite big ones, from 90 to 130 at the end of the cycle. We can see that there is various issues around during the cure cycle as well. We can see that there's various issues around thermal lag, et cetera, et cetera. So yeah, we have many issues to work out on this part. However, so to summarize, in this example, we've gone through thermochemical analysis, where we identified some issues with the thermal gradients and in our part, and clearly have some issues to resolve there regarding ensuring that our part achieves the desired cure cycle, whether that's by changing cure cycle itself, redesigning the tool, or potentially even redesigning our curing equipment. In the flow compaction analysis, we predicted the consolidation behavior, and notably the change in fiber volume fraction and the gradients in fiber volume fraction in our part. And then in the stress deformation analysis, we synergized these results. We combined the thermal history and the fiber volume fraction gradients, and we're able to predict the process-induced deformations in our part as well. So that is a full process-induced deformation workflow. I hope you enjoyed the tutorial. If you have, again, questions about this, please see the documentation or contact us. Of course, as I mentioned before, we do offer a full characterization services as well, and that's an imperative part of the simulations. And also advanced users who are interested in using the ANSYS ACP pre, highlighted down here to define their layups, please contact us as well. Although the workflow is very similar to what we've shown here, and it is covered in the documentation too. So again, thank you for your time. I hope you enjoyed this and look forward to working with you soon.